Okay, so today, so the main thing I'm going to talk about, in the main lecture I'll talk about how multiband works, which is the most common functional MRI. But today what I want to do is the first of two lectures about quantitative scans. So I'll talk about some methods today that are sort of semi-quantitative, and then on next Friday I'll talk about how we can actually directly get a quantitative number, like a T1 number. So before that, why do we want a quantitative scan? And so, what is the motivation for quantitative? So why are regular scans not quantitative? So, if you have a regular scan, you got a nice picture of the brain. There's gray matter and the white matter, but the actual numbers that you get, for a given. So here's a given, voxel. The number you get is really truly arbitrary. So, on our scanner, that number might be for, gray matter might be, say, 250. But if you take that same person, stick him in the magnet, and do another scan, a week from then, you'll get some other number. It'll be, around maybe 300. And why is that? Well, maybe the person, like I said, maybe the person left their big belt buckle on, and it changed the shim. And but if you go to another scanner, you might get, say, 11,000. So the scanners don't have the actual raw numbers coming out of the scanners are somewhat arbitrary, depending on exactly how they've set up their imaging program. So if you look at it, you can easily see that's the gray matter and that's the white matter, using your visual system analyzer, which is really good. But the actual numbers really don't have any direct meaning. So that's the first thing, is you just have arbitrary image brightness, brightness number. So it's a T1 weighted scan, so it's going to be weighted by T1, but it doesn't tell you what T1 is actually. So that's and so if you're comparing to another scanner or a scan on a different day, you have to sort of normalize things and make certain assumptions about the contrast in order to make some comparison. And that's how most research is done. Like 99.9% of research is done that way. But there's several other problems, and two of the big ones are uncorrected coil fall off. Now, back in the day when we used to have, 1 Tesla scanners and a quadrature head coil that was relatively big and kind of far away from the brain, this wasn't as much of a problem. But now we have these, setups where we've got these small coils. The small coils, they might be only something like about that big, and so these small coils are going to have several properties. So one property that I mentioned before is that they actually have better signal to noise. And why do they have better signal to noise? It's precisely because they have more of a local field of view. So they, as a result of picking up signals more from where the coil is, they pick up less noise from other parts of the brain, and that's fundamentally why they have a better signal to noise, because they pick up less noise from the rest of the brain. But there's another feature of these coils, and that is they're quite sensitive to exactly where the brain is relative to the coil, partly because of the way that because of this fall off. And so what will that do? So if you take, if you put somebody in the magnet, so here's a cross section of somebody in the magnet. So there's somebody in the magnet there, and say they're a relatively small person and they're centered in the magnet. In that case, and then here you have the coils here, and compare that to a situation where somebody, like I have a very long head, and so when I go on the magnet, it's not quite that long, but I'm quite long, and I kind of run into the top of the coil. And the back of my head can be pretty close to the coil. And so in a situation like that, what will happen is the actual brightness of the image when you get close to the coil will get a lot brighter. And we're talking like 100% brighter or 200% brighter, like 2 or 3 times. It can be 2 or 3 times as bright because you're closer to that small coil, and so you'll get an image like that has like this giant fall off in brightness. And so whereas somebody else will be their whole brain with a smaller brain that's more equally spaced from the coils will literally be like 1/2 or 1/3 as bright as the frontal lobe here. So that's a major problem, and we'll talk about several ways of fixing it. But let's also just talk about what kind of differences we're actually interested in. And so if you look at the gray matter versus the white matter. So if you take a voxel, somewhere in the gray matter, and then compare that to, a voxel somewhere in the white matter, you might have, a typical number might be, say, something like 120, and then this guy might be, say, 135. Like a 10% difference. That's a reasonable 10-15% difference is a reasonable difference here. So compare that to this 200% brighter. Okay. So this so the gray matter and white matter might be 10 15% on a good day, depending on your pulse sequence. So that's okay. That's a reasonable amount of difference in order to distinguish gray and white matter. But what about different areas? So if we take an area, there's an area in the cortex, called, MT. MT is if you come to my other course or look at it online, the MT is an area involved in motion perception. It's very heavily myelinated. The actual gray matter is myelinated. So there's obviously more myelin in the white matter, which is the coating over the axons that makes them conduct faster. But it turns out that in the gray matter there are differences in myelination, and that for a century that's how people recognize these areas. That's how they found, area V1. There's a lot of myelination in the middle layers of area V1, the first visual area. That's how you can sort of recognize different areas in the cortex. So what are some of the kinds of differences we're looking at? Well, MT is one of the most myelinated areas in the entire cortex. And if you look at another area, the angular gyrus, that's a very generic area, but basically, where are those things? Well, if we look at a brain, MT is kind of like about there, and angular gyrus is about there. So this is, this is in a human brain. That's about where MT is. and this is about where the angular gyrus is. So they're right next to each other, just a centimeter apart, something like that. So what is the difference between these two guys, MT and angular gyrus? So that's like the most myelinated versus one of the least myelinated. It's like 4% difference. So so that means most areas are going to be in the range of 1%, and we have these 200% brightness changes just in our image. So that's another problem. But there's a third problem, which is uncorrected variations. Variations in B1. So the problem here is that if you look at a relatively lower Tesla, like say 1.5 Tesla, and you look at the wavelength of the 63 or 63 megahertz signal, RF signal. So what is the wavelength? The wavelength is going to be quite big, something like it's like an FM radio station. So this is the wavelength here of those RF radio frequency waves. So if you go up to higher, that's a little bit bigger than it is, but it's like a meter or something like that. So if you go up to higher frequencies, so it's the frequency is exactly proportional to the Tesla. So from our very, very first equation, and so if you double the Tesla, you'll have the frequency. And so what happens? You start to get things kind of more like your microwave. So what is the frequency of a microwave? Well, this is the frequency here was like about 63 megahertz. Our 3 Tesla is about 123 megahertz. Your microwave is 2.4 gigahertz. So that's 2,000 megahertz. So what happens in the microwave? You get hot spots. You stick something in there, something gets really hot, and something else isn't as hot. And what causes that? Well, the radio waves go in, and if they're about the same size as the actual object that you're stimulating, there's going to be a tendency for them to bounce around inside the object, like a resonant cavity. And this starts to happen already so this is wavelength 1 Tesla. At 3 Tesla, it's going to be 3 times the it's going to be 1/3 the wavelength, and so it's going to start to resonate around inside the cavity of your head. At 7 Tesla, it's worse. So at 7 Tesla, this is a story I always tell. If you stick your feet in the body coil and you have your head out of the body coil, and you do RF on your feet, it will resonate around in your body and make a signal come out of your head. So that's a bigger problem. So that's about the B1 field. And what is the B1 field? That's the field that's actually sort of rotating around in this plane, perpendicular to the bore. So this guy's the B1. So at 3 Tesla, the kind of problems we have are something like a 25-30% variation across the head. Now, that can be, pretty substantial, because remember, like if you look at something like the gray matter as a function of flip angle, looks something like that, and the white matter looks, something like that. This is white matter. And what are these numbers here? Well, these numbers say this is like, 7 degrees. And if you go down to like, say, about 6 degrees, or 5.5 degrees, you actually have no contrast at all. And so flip, when you say 25% variation, you mean 25% variation in the actual flip angle that's caused by an RF pulse. So you do an RF pulse and you say that this is supposed to be a 7-degree RF pulse on the basis of figuring out what the power was for a 90-degree, because at the beginning you sort of like figure out like what is the pulse that gives me the bigger signal. That's what we define as 90 degrees. But that's averaged across the head. And so some parts of the head are going to be off by 25%. That's a lot. That's enough to completely flip the contrast. So that's another problem. Like, how do we fix this? And I'll talk about that next. There's ways to fix this one too, to try to actually sort of compensate for the fact that we haven't done the same flip angle throughout the entire head. So that's pretty much the kind of the motivation. And what is the if instead we had something that was actually T1, so in other words, like if the number coming out of here, was actually T1, then what we could do is we could do a scan on somebody and then do a scan next year, and we could say, well, Bill, your T1 has gone to hell. You really have to sort of start improving your diet or like stop drinking because you could actually see this difference in an actual number, from year to year. Or you could compare a different scanner. Like, what if the scanner manufacturer makes images that have like, numbers of 25,000? Well, that's just like an irrelevant number. You could actually get a real T1 number out of there. And so it'd be a more diagnostic thing that would allow you to more directly compare scans, taken at different times. Because what happens right now is, a radiologist would just look at the scan and then just say like, well, it looks, there's a little more shrinkage, or, the gray-white matter contrast doesn't look quite as good, but, we'll just kind of eyeball it as opposed to actually just having a real number. So that's the motivation for a quantitative scan. And this is not a new motivation. People have been thinking about this for 30 years, trying to figure out ways of doing it. And what is the problem with doing this? Well, as you can imagine, the problem is we've got to collect more data. And so the problem is, if we just collect one scan, we're just going to have some numbers, and there's no way of, just from that one scan, since there's multiple things affecting it, there's no way we can sort of fish those apart, because we've only got one data point. And so all of these things require some kind of additional data collection. Now, the problem is that's going to take more time, but some of the additional data collection is pretty quick, and so we can only take maybe an extra 5% of scan time, and so that would make it more, more practical to implement. And so we'll talk about I'll talk about a couple different, talk about 3 different. So we'll talk about sort of this is something that we have on the scanner that talk about that one, PreScanNormalise, and then also T1 divided by T2. Another method of trying to normalize things. And then I'll talk about MP2 range. Which is another one that's really a lot closer to a quantitative scan. So first, the PreScanNormalise. So that's one you can just tick that on almost all the pulse sequences on our scanner. And so what does that do? So what this does is before the real scan runs, what happens is a very quick and dirty scan that is collected through the body coil. So here's your magnet, and you've got the so-called body coil in there. So it forms the bore. Actually, the body coil is just right beyond the actual sort of physical central bore of the magnet. So that's the body coil, and it's called the body coil because you could image the body through it. But it turns out nowadays we don't even image the body through the body coil anymore. We have a bunch of small coils, like the spine coil. It's not a single coil, it's a whole set of like 32 coils that runs down the bed as you're just like lying back on the bed in order to get better signal to noise. But the body coil is still used for stimulating, for transmitting into the subject. But you can also receive from the body coil. So there's no reason you can't receive from the body coil. You don't generally do that nowadays because the signal to noise isn't as good. And why is the signal to noise bad? It's not because the body coil is a bad receiver. It's a great receiver. It's actually a much better radio wave receiver than the small coils. It's a big antenna. The problem is it's picking up all junk from the whole rest of the room and other parts, and your kneecap and everything, and you're trying to record from the brain. So there's nothing wrong with the signal coming out of the body coil. It's a great antenna. It's just that it's picking up a lot of noise from other parts. And so if you look at the image that you get from a body coil, you can make an image from the body coil to receive from the body coil. You can transmit from the body coil and also receive from it. You see the image looks a lot noisier, but it's much more uniform because it's much further from the thing that you're recording. So the body coil is like a big body coil like that, and you've got this little head inside of it, and so it's not going to have this coil fall off problem. And so you just record a quick and dirty image from the body coil. So basically, this guy is PreScanNormalise. Spell it British because it's spelled British in the scanner interface. So if you do PreScanNormalise, you just collect image received with body coil, also transmitted. Now it doesn't have to be a very high resolution image, and that's why you can sort of get away with recording something that's very very quick. And so why doesn't it have to be a high resolution image? Because if you look at the brightness differences that come from, if you happen to be really close to this coil over here like that, the image is going to be brighter right around that coil, and it might be 200% brighter than the rest of the brain, but it's going to fall off nice and slow. And so when you actually look at you look at this field, this brightness field, it's nice and smooth. And because it's smooth, you don't have to collect very big voxels, like any old voxels, like that big enough, something like that. That's big enough to give you enough information to calculate that relatively smooth field. So, and the advantage of this is it's uniform brightness, uniform coil, fall off. And then you just go ahead and collect your regular scan. So it doesn't have to be very high res. And then now we've got the same object but recorded with these brightness varying scans. And so you can see there's various kinds of hacks you could do, like smooth the actual image that you get out about the same smoothness as this one, and then try to divide by this image, especially if it doesn't have very much gray-white contrast. So like say this, say you take an image that doesn't have very much gray-white contrast, and you've got gray and white contrast in the high-resolution image. If you divide by this one, it will essentially remove that brightness signal. And there's little more complicated things you could do to make it work pretty well. But that's a big help, because that will sort of flatten out your image. It's not really quantitative, but it will at least sort of make another measurement that you can use to correct your measurement. Now, you could obviously just use a computer program to try to flatten out the image afterwards. And if you look at any of the computer programs for processing brains, they've got a whole series of ways of trying to estimate what that sort of brightness variation is and cancel it out. But it's always better to have some more data. So, I mean, you can fix it. There's various ways of fixing it post-hoc without any data. But if you've got some actual data, that's better. And so in general, it's better to. And then you could do some normalization after that, after you've sort of like fixed the main problem with some data. Okay, so that's one straightforward way to do it. Another way to do it, which has been heavily used in the Human Connectome project, is T1 divided by T2. So if we take an MP RAGE, that's a T1 weighted image. So that's T1 weighted, and that's the one that we are using to distinguish gray and white matter typically, because there's a big T1 difference between gray and white matter. And then we take another image like that one that I talked about, like the really fast spin echo. So it's like a space scan. You can make a space scan proton density weighted, but you can also make it T2 weighted. So if you make it T2 weighted, there's no difference between gray and white. So gray matter is about the same as white matter. So in a T1 weighted scan, white matter is bigger than gray matter. It's lighter. It looks like. Notice it's reversed. White matter is brighter than gray matter because the T1 of white matter is shorter than gray matter. So if you did it in terms of T1, gray matter has a higher T1, but it's dimmer because this had faster recovery, and so you got more signal. So it's kind of, so a T1 weighted image is actually an inversely T1 weighted image. So if you actually looked at, the gray matter number for T1 should be higher than the white matter number for T1. Okay, so and then if you just divide the T1 image by the T2 image, that's going to get rid of a lot of the variation in brightness due to the coils. Now, there's several problems with this, so it doesn't deal with B1. So there's still these B1 differences that are causing differences in contrast in different parts of the image, and then it also has the problem there's different distortion. So, and why is that? Well, the flash-like scan, the MP RAGE type scan, is a gradient echo. And so that means it's T2 star. And so it's not correcting static field offsets because the echoes that come out are all T2 star weighted. And so they've got the star problem from fixed B0 offsets. So different distortion from B0. So this one was the was the B1 from the RF transmit, but the B0 is just like a static, different distortion from B0 defects, so different parts of the brain are going to have slightly different B0s, and those will be translated into spatial distortions. So remember, that's the relevance of this is that causes, turned into space, turned into spatial distortion. And now the spin echo, which is the space one, that one's going to be a T2 scan, and so that's going to correct the static field offsets. And so what's going to happen is you'll have two images that are slightly differently warped. And so when you divide one by the other, you're going to get problems in places where the warp is there. Now there's ways to fix the warp. You could collect a field map in order to try to fix the warp in the gradient echo image, and then that would help. And then before you divided by the T2. But as we mentioned before, that's another scan. So you're collecting another scan to get more data. Okay, and so there's other ways to fix it that we can talk about, that I'll talk about next time, to actually essentially collect scans of all the same kind, so you don't have this spatial distortion difference, and then also try to estimate what the B1, what the actual local B1 is, and factor that whole thing in. Okay, so that was sort of just collecting quick and dirty scans through the body coil in order to sort of normalize the brightness, or collect another scan, a whole nother scan, and divide by it. And then the last one, or we could just actually collect two scans all at once, and that's MP2 rage. So last time, I don't know, a couple times ago, we talked about how MP rage works, and MP rage was this gradient echo sequence that it's kind of like a weird sequence where you had this inversion pulse, and then you do a flash type scan. So the flash type scan was a fast gradient echo, a bunch of low angle flips to record the data very quickly, and with the hope that you would kind of more or less wipe out the signal after each little low angle flip. So that's the spoiling. So it was like spoiled grass, or flash, so that you use a bunch of low angle pulses to not kill your longitudinal magnetization, and then you try to clean the slate after each pulse. So, but MP rage was that combined with an inversion pulse. And so that's what MP2 rage is, except that you record two complete volumes of data after each inversion. So what this one looks like is we've got the RF up here. So this is MP2 rage. We have this on the scanner too. MP2 rage, 3D. It's a 3D scan. So the first thing is the RF in, and here's the three gradients, and here's the signal coming out. So gradient, like the slice direction, and the phase encode direction, and the readout direction, and the signal that comes out. So the first thing is we do a high quality inversion. So there's different ways of doing an inversion that take varying amounts of time. So So the first thing we do is an adiabatic 180. So why don't we do that all the time? So if you do if you do a hard pulse or just even a sync pulse, that's kind of more like a hammer. You're just sort of banging on the brain. An adiabatic pulse means like a kinder, gentler pulse, where you slowly sort of take your time and sweep all the protons into alignment with each other. And what's an example of a pulse like that? One way of doing it is to ramp the frequency of instead of just playing out this little blip of a pulse, like a sync pulse, where you make a little variations in the transmitter amplitude, and that when you Fourier transform it turns into a band of frequencies. Instead of doing that, if you're trying to invert, what you can do is just ramp the frequency of the transmitter, slowly ramp it. And we'll talk about that a little bit later, but that's one way of causing an inversion in the magnetization, is to slowly ramp the frequency of the so start off resonance, come through resonance, and then go off resonance in the other direction. So that actually, surprisingly, that will actually do a really good 180. And since we've got to wait a little while for the inversion, for the recovery of the magnetization before we start recording, that's okay. We can afford to do an expensive pulse like that in time. If we didn't have to wait after it, then we couldn't afford to do that. So we wait a little while. So there's a little bit of gap in time while we're waiting for some recovery, because remember, we're trying to sort of wait until we get, say, gray matter about zero and white matter recovered some above zero, so that there's a big contrast difference between gray and white matter. And then we start doing our flash type readout. And so for that, we just do a whole series of alpha pulses, hundreds of them. So these are all low flip angle, 7 degrees or whatever. And then we're trying to read out the data as absolutely quickly as possible. And so we have to do some phasing coding on the partition direction. So that was, remember, that's the second phasing code, because it's a 3D scan. And then some phasing coding on the regular phasing code direction, which is not different at all, except it's just a different direction in real space. And then we do a readout, we go to the left side of K-space, and then do a readout like that. And collect one line of K-space. And then I mentioned last time with MP-Rage is that it's a weird mix, because the magnetization is recovering, and it's not a steady state scan the way that flash is. But then in addition, it's kind of you rewind, you kind of fix all the two phase encode direction magnetizations, as if you were doing something more like a grass type scan, where you're saving the magnetization. So remember, there was two types of fast gradient echo. You could have coherent or incoherent. So coherent, this is more like the coherent one, where instead of trying to squash all the magnetization that you've got at this point, the transverse magnetization. And so what is that? That would be like, at this point right here, you're going to get, there's going to be an echo. So there'll be an FID from the alpha pulse, but then here's the echo that you're recording. But at this point in time, there's still some transverse magnetization left, like that. And so we could fix it all up, put it all back into the center of k-space. Now, we know that in the case of the coherent scans that sort of fix it all up, so like, we'll do it this way over here and then do whatever you just undo whatever you did, that changes the contrast. But this still looks like a regular incoherent scan. And so why is that? It's because we haven't fixed the readout. So this is the partition direction or second phase encode direction, and this guy is the phase, and this guy's the readout. So we didn't fix the readout. So we left ourselves all the way off to the right side of k-space, and that's sort of like spoiling it because you're wrapped up to 128 cycles of spin phase, and the signal is pretty small. But we fixed these to sort of like save some of the magnetization in the other direction. So it's a motley sort of weird kind of pulse sequence with multiple things going on. Okay, so then we keep doing that, etc. So immediately do another one here, and there's another fixer there, and another phase encode. Pick a different phase encode, and fix that guy, and then do another readout like that. Get another echo because we need lots of echoes, and then etc. And then we wait until we get to the center of k-space. So there's going to be a couple hundred of these, and then eventually we get to the center of k-space. So here's the center of k-space, and so that'll be again one of these, and another one here, getting sloppier. And what's the center of k-space? The center of k-space is going to be the middle, right? So it's going to be that one, and so it's going to be that one. So just pick out the middle one, which is no gradient because that's the actual center of k-space. Okay, so there's the center of k-space. I'll dot that one because we're actually picking out the middle. And then we still have to go to the left side of k-space and read it out, but this guy will be the biggest echo. So this is the center of k-space. But it's the first center of k-space. So this is the first center of k-space. So what's going on in the overall picture? So the overall picture is that we are, so at this point, if that was a good 180, you shouldn't get much of a signal out of it. And so if we put this down here, so what's going on here? So we started off sort of more or less at MZ0, and then we did a 180. So here's 0. And then we start recovering for a while. We wait. So, and this is a pretty big gap. So we wait for a while and start recovering. Don't record any data. And then we start doing a bunch of alpha pulses. So here's those alpha pulses. And there's like about 100 of them. I only drew a couple there. And this is the first center of k-space. So first center of k-space, well before we've gotten up to 0. So there's 0. This is about MZ0, and this is about minus MZ0. So since this is relatively soon afterwards, and we haven't really recovered, we're going to get something that looks like a proton density weighted scan. But then what we do is we wait a little while and then do the whole thing again. And so now collect a whole nother set of case-based data. So this is, maybe make this one in the center here. Make this in the center so it's kind of symmetrical. So we recorded that one pretty early on. So basically this is, this is our first case base. So we're collecting two complete case bases, like repeating. And then here's our second case base. So what do? We just, collect the rest of our first case base. And then we wait a little while, and then start collecting our second case base. And so now, back to a bunch of alpha pulses, etc. And then wait until we get to the center of case base. So, and then, here is the actual center of case base again. So this is our actual center of case base. And in this one, we want the gray matter to have recovered to 0 and the white matter to have recovered above 0. So our hope is that, when we record the second center of case base right here, then the hope is that we actually have our, say our white matter recovered above 0, and then we've got another one right below it like that, where our gray matter is still at 0. And so we get a lot of contrast between the gray and the white matter. And so that one will correspond to our second big echo. So here's our second time through case base. So this is second center case base. So we end up with two complete images. So this, this guy goes here. This guy, goes here. And so this is, this is all filled in. So we got like a zillion pulses here. So every time we do one of these, got another one of these, and another set of fixers. So you can see it's just a rat's nest of RF pulses, and here's some little recording of a small echo. That's a small echo because it's out in the edge of case base. So basically now we just have like two complete case bases, and so with two different inversion times. So basically there's going to be one inversion time here, and that's time inversion effective, because remember, all of these guys have different inversions, but just the center of case base inversion is, time inversion effective 1. And then this guy is going to be time inversion effective, because there's all different inversions for all the different parts of case base 2. So, and this one will give us a T1 weighted image. This one will basically give us, proton density. So this one will look like, proton density. This one will look like T1. So now we have two complete images. And so what do we do with these two complete images? So what we can do, you can just do a quick and dirty divide, but it's a complex value divide because we've got complex data. So the first thing we could do, if you want to get a number that's between like minus 0.5 and 0.5, we could multiply these two complex numbers by each other. And if you just want to square a complex number, like square the amplitude of a complex number, what we do is we usually take that number and multiply it by its complex conjugate. So this is, what that means is flip sign of imaginary part. So if you flip the sign of the imaginary part and then multiply it by itself, and what are we multiplying there? We're multiplying our the signal from time inversion, 1 times the signal from time inversion 2. These, TI effective 1, TI effective 2. And then divide that by the amplitude of TI1. So I'm putting the vector there to mean it's the complex value squared plus the amplitude of the other one, TI2 squared. So both of those are squared. So if you do that, you'll end up with, you can work it out, but you'll end up with a number, just the number that goes from 0.5 to minus 0.5 to 0.5, and you can convert that to T1. So you need a little bit of extra math, but you could convert it to an actual T1. And we have this on the scanner if you want to play with this one. It doesn't take very much longer than a regular MP RAGE, because what you're doing is, in a regular MP RAGE, you'd wait longer before you started recording for some recovery. But here you can, I exaggerated the amount of time here, you can essentially start this proton density weighted scan very early using time that you would have just been sitting around in the regular MP RAGE. And so it doesn't take very much longer than a regular MP. It does take a little bit longer. But what's the problem with this? So say we do this thing. So one of the problems with this is that, let's slightly make a hole here so I can, a little more room. So one of the problems with this is that if we, look at the cortex, so here's the cortex here. Cortex looks really good. So there's the cortex. Gray matter and the white matter look really good. And the dura is pretty good. That looks really good. And then we get up to the skull. Now the skull doesn't have much signal in it. And so if this is the skull here, when you look at the skull, you can see the marrow of the skull. There's some signal in the marrow of the skull, but the bone of the skull has such a short T2 that there's no signal. It's black, so the CSF is black, but there's a big signal coming out of that. It just has, it has long T2 values, so it ends up in a T1 weighted scan being black. This black is different. That black is different because there's no signal coming out of the skull. There's this big signal coming out of the skull, but it came out and decayed away before I got a chance to record it. And so what happens when we do this calculation here? So when we do this calculation here, we divide like a small noisy number by itself, and what do we get? We get a bunch of junk. And so what happens is when you process this image, you'll see there's just that complete speckled black and white noise in here. It doesn't look like, it's not black anymore. And then we get out to the little fat layer. That one's got a signal again, and then we get out to the skin. But when we get out to the air, complete mess. It's just like speckled black and white, you know. So if you take an image like this, even though this image is much better, it's much more quantitative, and just feed it into a program that's designed to segment the brain, it's not going to work because there's just all this junk. There's a bunch of junk in the skull and a bunch of junk out in the air. So you could fix that. So you could take the proton density weighted image, which does have black out in the air, and then you could use the proton density image to mask out all that junk and maybe try to find the skull. It's a little harder to find the skull because then you have to somehow find out where the skull is in order to be able to mask it. The air is relatively easy because you could just sort of turn off anything that's black outside because there's some black stuff in here, and the proton density image is not going to distinguish that black from that black, but if you just like shrinks like a surface onto the skull, we can sort of like just, you know, get rid of the noise outside the skull. So there's various problems with it because we have these low signal to noise areas that generate noise. But in general, you're going to get a much better number that you know, if you're trying to segment gray from white matter, you're going to do a better job because these will be like real numbers that don't vary across the brain. Okay, I'm going to end the lecture there, Stan, and before I go over,